Hello and welcome to Stories of Science. Here, we look back on humanity's long journey to understand the world. The questions, the failures, and the breakthroughs that slowly changed how we see the universe and ourselves. We tell science as stories. The physicist who forced the universe to behave, how Wolfgang Pauli built the hidden rules behind reality. Picture this. A theoretical physicist walks into a lab. He hasn't touched a thing yet. And boom, something breaks. Not metaphorically. The lights flicker. A coil smokes. Glass cracks. Everyone freezes in that universal lab moment of panic. Okay, who touched the equipment? And slowly, almost ritualistically, all eyes turn to the same person. Him. Colleagues would later joke, only half joking. The moment he gets near an experiment, probability itself starts acting funny. Physics history even gave this running gag a darkly comic name, the Pauli effect. The man at the center of it was Wolfgang Pauli, a theoretical physicist rumored to bring catastrophic luck to laboratory hardware. It sounds like an urban legend, but in European physics circles of the time, it became a shared superstition. If you want your apparatus to survive, maybe don't invite Pauli. Of course, science does not recognize humans with built-in explosion fields. But the joke survived for decades, and that tells you something important. This was not an ordinary figure. He was so intimidating intellectually that blaming broken equipment on his presence felt easier than admitting, "Yeah, I probably wired that wrong." Pause for a moment. If the story ended there, it would just be one of physics' favorite inside jokes. But here's the twist, and it's a big one. The same man jokingly blamed for experimental chaos wrote one of the most unbreakable rules in quantum physics. A rule that dictates how electrons arrange themselves, why atoms don't collapse, and why matter has structure at all. In other words, the lab might not have trusted him, but the universe absolutely does. That's not irony, that's one of the great dramatic tensions in scientific history. A man who rarely ran experiments ended up defining the hidden order that makes experiments possible. Every time you see why chemical elements behave differently, why atoms stay stable, why materials have structure, you are watching his rule quietly do its job. So when people say, without him, modern physics would wobble, that's not exaggeration. We're not talking about slower progress. We're talking about rewriting the framework of how matter is understood. And the real story isn't just genius writes equation. It's about a critic with zero tolerance for sloppy thinking, a mind that dismantled weak logic on sight, a physicist who could make colleagues rethink their careers, becoming one of the architects of order in a chaotic new science. So the real question isn't about exploding lab gear. It's this. How does someone with a reputation for intellectual demolition become the author of one of nature's strictest rules? That journey starts in Vienna not with broken equipment, but with a young mind already stress-testing reality itself. Early 20th century Vienna was alive with music, philosophy, and debate. Waltzes filled concert halls. Cafes buzzed with ideas. And in one household, dinner conversations sounded less like family chatter and more like a seminar. Imagine sitting at a table where the casual topic is this assumption logically consistent? Welcome to Pauli's childhood. Some kids grow up on fairy tales. Pauli grew up inside a laboratory atmosphere of ideas. His father was a scientist, his social circle packed with academics, and intellectual rigor wasn't a performance, it was the background noise of daily life. Where many households ask, "How was school today?" his might ask, "Does that argument actually hold?" And here's the key. He wasn't pushed into brilliance. He genuinely enjoyed thinking. Very early on, people noticed something uncanny. He had an almost allergic reaction to logical errors. Not the usual good at homework intelligence, but a radar for inconsistency. A teacher writes a derivation. Pauli looks at it for a moment. That step doesn't follow. Not attitude. Accuracy. Suddenly classrooms developed a quiet tension. Teacher explains. Students copy notes. Pauli runs real-time verification in the background. Later physicists joked, if Pauli nods, your argument probably survives inspection. Understand what that means for a young scientist. Most students learn physics by solving problems. Pauli learned physics by interrogating problems. Others asked, "What's the answer?" He asked, "Is the question even valid?" That's not contrarianism. That's structural thinking. By adolescence, this ability turned dangerous. He wasn't just correcting classwork. He was spotting flaws in advanced textbooks, not typos, but structural weaknesses. Picture a teenager calmly saying, "This derivation isn't rigorous," and being right. At that point, educators realized this wasn't high performance. This was a different layer of thinking. He wasn't absorbing knowledge. He was testing its integrity. In an era when many believed classical physics was nearly complete, a young Pauli was already instinctively doing something radical, checking whether the universe's description actually held together. That habit would later become physics' unofficial quality control. New theory appears? Run it past Pauli. If it survives, it's probably solid. So here's the turning point. Was this young critic tearing down order, or preparing to build a deeper one? The answer arrives in the roaring 1920s, when quantum theory bursts onto the scene. The 1920s were a fireworks show of equations. New ideas exploded across journals. Predictions dazzled. But mixed in with the brilliance were shaky assumptions, beautiful math hiding fragile logic. In the corner sat Pauli, notebook open, expression calm like a hunter waiting for movement. In early quantum physics, everyone was trying to decode reality's operating system. Some theorized boldly, some calculated endlessly, and one man specialized in identifying where things fell apart. That was Pauli. Not casual criticism, surgical precision. A phrase began circulating. If Pauli says, "Interesting," you might have something. If he says, "Wrong," go back to work. If he says, "This isn't even wrong," that was intellectual annihilation. The line became legendary not because it was cruel but because it was devastatingly accurate. Pauli's real talent wasn't just spotting errors. It was showing how you could have failed more intelligently. One young researcher once presented a new theory with visible pride. Pauli listened quietly. Silence filled the room. Finally, "This doesn't work, and worse, it's not even creatively wrong. Air temperature, 0 Kelvin. Years later the presenter admitted, "I wanted to quit physics. Then I realized he was forcing clarity." Pauli's critique cut like a scalpel. Sharp, yes, but aimed at removing illusion. That's why even physicists who feared his commentary respected him deeply. If your theory survived Pauli, it probably deserved to live. He crossed intellectual swords with giants like Werner Heisenberg, Niels Bohr, and Albert Einstein. They all understood. Discussing ideas with Pauli was like stress testing a bridge. If it stood, it was real. He didn't criticize for sport. He feared something deeper. Physics drifting toward elegant nonsense. During quantum theory's most chaotic years, Pauli functioned as intellectual gravity. Every idea had to answer. Where's the logic? Where's the evidence? Did you really think this through? As the saying goes, measure twice, cut once. Pauli insisted physics measure 10 times before declaring victory. And in doing so, he helped transform a storm of speculation into a discipline strong enough to carry modern science. The explosions in labs were jokes. The explosions in understanding? Those were real, and Pauli stood right at the center, making sure the foundations held. The greatest danger for a genius isn't having wild ideas. It's creating a standard so high that nobody else gets to be careless anymore. That was the paradox of Wolfgang Pauli. He didn't just challenge theories, he challenged sloppy thinking, and in doing so, he raised the intellectual bar of an entire era. Only ideas strong enough to survive ruthless criticism were allowed to live. Quantum physics needed dreamers, but every frontier also needs a gatekeeper, and Pauli stood at that gate. He made physics not just bold, but disciplined. Here's the twist. The man famous for tearing apart other people's mistakes would later write one of the most unbreakable rules in modern science. But before that breakthrough, his life cracked. When logic isn't enough. By the late 1920s, Pauli's personal world started collapsing. First came the death of his mother, not just a loss, but the loss of the emotional anchor that held his inner structure together. For someone who trusted logic more than feelings, this wasn't a wound you could calculate away. Then his marriage fell apart almost as quickly as it began. Suddenly, the man who could dissect quantum paradoxes found himself facing something that refused to obey equations: grief. Picture the contrast. Daytime, Pauli debates the foundations of quantum mechanics with surgical precision. Nighttime, he sits alone in a bar, trying to quiet a mind that wouldn't stop spinning. Colleagues later described him as a machine still running, but without a compass. Even the sharpest minds hit turbulence. And as the saying goes, you can't reason your way out of a storm you didn't reason your way into. The turning point didn't come from physics. It came from psychology. Pauli was introduced to Carl Jung, a man exploring the architecture of the unconscious mind. What followed was one of the strangest collaborations in scientific history. Jung didn't ask Pauli about equations. He asked about dreams. And Pauli, methodical as ever, began documenting them. Symbols, geometric structures, recurring numbers, strange myth-like imagery. These weren't random fragments. They showed pattern, order, structure. Jung was stunned. Here was a mind revealing that rational thought and the unconscious might not be enemies, but partners speaking different languages. Pauli began to suspect something radical. Maybe reason isn't isolated. Maybe the unconscious isn't chaos. Maybe both follow deeper laws. Their discussions expanded into territory few physicists dared to enter: symbolism, synchronicity, the relationship between mind and nature. Not mysticism, exploration, a recognition that creativity often comes from places logic alone cannot reach. And slowly, Pauli rebuilt himself. The chaos didn't disappear, but it became legible. For a man obsessed with structure, that realization was a kind of healing. Even the mind has patterns. Which raises a haunting question. If quantum theory reveals nature's hidden framework, does consciousness have one too? We're still chasing that answer. The quiet war over reality. Rewind to the birth of quantum mechanics, and physics conferences felt less like meetings and more like intellectual duels. Polite voices, explosive implications. The debate wasn't about calculation errors. It was about reality itself. Standing in that arena were three giants: Albert Einstein, the defender of a deterministic universe; Niels Bohr, who redefined what it means to observe; and Pauli, the razor-sharp critic who wouldn't let fuzzy thinking survive. Einstein insisted the universe must be lawful and precise. Probability, he argued, was just ignorance in disguise. Bohr countered with something more unsettling. Physics doesn't describe reality in isolation. It describes how we interact with it. Reality isn't revealed, it's negotiated through observation. Pauli stepped in like a logic referee. The problem isn't that nature is strange. The problem is that we're using outdated intuition. In plain English, maybe the universe isn't breaking the rules. Maybe the rulebook changed. At the heart of the debate sat the wave function. Tool, reality, probability map? Einstein doubted its completeness. Bohr embraced its limits. Pauli clarified. It doesn't describe things. It describes possibilities. Reality, then, isn't a single track. It's a field of potential, and what we observe is one path taken. These debates weren't academic sparring. They were redefining what existence even means. And no one won. What survived was something more important. Quantum theory works, but what it means remains open. Science admitted something rare. Success doesn't guarantee understanding. And that humility became part of modern physics, the rule that holds the world together. Now imagine physics in the 1920s facing a terrifying puzzle. Why doesn't matter collapse? According to existing calculations, electrons should spiral inward and crash into atomic nuclei. No stable atoms. No chemistry. No solid world. In theory, existence itself looked unstable. Enter Pauli asking a question nobody else framed properly. What are electrons allowed to do? His answer wasn't a new force. Not a revised orbit. But a rule. Simple. Absolute. Non-negotiable. No two electrons can occupy the same quantum state. Think of it like assigned seating in a packed theater. Every seat has a number. One ticket, one seat. No squeezing in. No duplicates. No cheating. Electrons obey the same discipline. Each carries a unique identity label, energy level, spin, quantum numbers, and no two are allowed to share. Once this rule entered physics, chaos snapped into order. Electrons formed layers. Atoms stabilized. Chemistry suddenly made sense. Matter gained structure. Your desk is solid not because particles behave nicely, but because they must follow rules. Even stars depend on this discipline. White dwarfs resist collapse because electrons refuse to stack infinitely. Matter occupies space because electrons won't pile into the same state. As the saying goes, order isn't optional, it's survival. The universe stays stable not by chance, but by enforcement. If electrons could cheat, atoms would fail, structures would dissolve, reality would wobble. Pauli didn't make electrons behave better. He defined where they're allowed to stand. And that rule, invisible yet absolute, became one of the pillars of existence. Closing reflection. Pauli's legacy isn't just a law. It's a mindset. Relentless questioning. Demanding clarity. Treating ambiguity as an invitation, not an excuse. Science isn't a machine that produces final answers. It's a process refined by doubt. And Pauli embodied that spirit. He proved something profound. Dreamers push boundaries. Gatekeepers preserve integrity. And progress needs both. The man once known for catching mistakes ended up writing one of nature's strictest rules. He made electrons follow discipline, and scientists follow rigor. Because in the end, the universe doesn't reward confidence, it rewards consistency. And as every good physicist learns, reality doesn't bend for convenience. It only responds to understanding. When the rule was first introduced, it didn't look revolutionary. It felt local. A patch. A fix for a stubborn atomic puzzle. That was it, or so it seemed. But history has a habit of hiding earthquakes inside small ideas. Drop a pebble into still water, and the ripples travel farther than anyone expects. That's exactly what happened. The first ripple hit the atom itself. Early atomic models were elegant sketches with missing logic. Electrons orbiting nuclei, fine. But why layers? Why stability? Why didn't everything collapse inward like a bad simulation? The answers were fuzzy, almost hand-waved. Then the picture snapped into focus. Electrons weren't roaming freely. They were being forced into structure. Inner levels filled first, outer layers stacked in order, and stability emerged not from motion, but from enforced arrangement. Atoms weren't fragile guesses anymore. They became disciplined quantum systems. Stability wasn't a lucky calculation. It was order doing what order does. And as the saying goes, rules don't limit the game, they make the game possible. The next ripple traveled straight into chemistry. Suddenly, the periodic table didn't look mysterious, it looked inevitable. Why do properties repeat? Why are some elements hyperreactive while others barely participate? The answer kept pointing to the same place. Electron seating. Atoms shake hands based on how their electrons are arranged. Chemical bonds are less about attraction and more about negotiation, particles finding allowed configurations when sharing is forbidden. No two electrons can occupy the same quantum state, so they improvise structure. Molecules form. Reactions unfold. Complex matter appears. The chemistry we interact with every day isn't random assembly. It's quantum order expressing itself on a larger stage. Water flows. Metals conduct. Air supports life, all because electrons obey placement rules. Not coincidence. Constraint. Then came a deeper ripple, one that rewrote how physicists think about crowds of particles. Classical statistics assumed particles were stackable. Put as many as you want in the same state. No problem. Reality disagreed. When particles must obey occupancy limits, collective behavior changes completely. Now you get a new statistical framework, one where arrangement matters as much as energy. Suddenly, phenomena that once seemed unrelated fall into a single narrative. Electrical conduction, low-temperature physics, dense stellar matter. These aren't isolated quirks. their group behavior under constraint. From a single electron, to atomic architecture, to macroscopic matter, a clean causal chain appears. And here's the twist. All of it emerges not from adding forces, but from forbidding certain possibilities. Sometimes structure is born not from freedom but from limits. Or as the old saying goes, a river has power because its banks hold it in. Physics quietly agrees. When this quantum seeding rule left theory and entered technology, it didn't stay abstract. It went straight into machines, into materials, into the invisible backbone of modern civilization. The first major transformation happened in semiconductors. In classical thinking, electrons wander like loose crowds. But inside solids, they obey layered energy rules. Bands form, gaps appear. Conductors and insulators aren't vague categories, they're consequences of quantum structure. When engineers dope a semiconductor, they're not just tweaking material, they're rearranging electron seeding charts. A transistor switching on isn't mechanical motion, it's quantum order scaling up. Every flowing current is electrons following rules they cannot break. Which means, your phone, your computer chip, fiber optic communication, they're not just circuits, they're choreography, electrons dancing within strict boundaries. Modern computing rests on a principle articulated by Wolfgang Pauli: nature enforces order at the smallest scale. And every device you power on is proof. The ripple continued into material science. Before quantum understanding, discovering materials was expensive guesswork. Now scientists can anticipate behavior. How electrons fill structures, how atoms arrange, what properties emerge, why metals conduct, why ceramics endure, why superconductivity appears. The common thread is collective electron discipline. Change the arrangement, change the behavior. Material design evolved from trial and error craftsmanship into predictive engineering. We stopped just finding matter, we started designing it. Even particle physics and astrophysics feel the impact. Some particles are allowed to share states, others absolutely refuse. That distinction shapes matter itself, from subatomic interactions to the stability of dense stars. Extreme cosmic environments obey the same occupancy discipline, different scale, same rule. From the quantum realm, to everyday technology, to the architecture of stars, a single constraint echoes across reality. So when you press a power button and a screen lights up, what you're seeing isn't just electricity, it's quantum order at work. Every functioning device is electrons honoring a rule older than your hardware. And that's not poetic exaggeration, it's engineering reality. But the deepest ripple wasn't technological, it was philosophical. This rule didn't merely describe motion, it revealed something unsettling. Stability often comes from limitation. That insight reshaped how scientists think about theory itself. Does a formula describe reality, or construct a language for understanding it? After the quantum revolution, physicists recognized a tension. A theory can succeed mathematically and still leave interpretation open. That tension isn't weakness, it's vitality. In this tradition, doubt isn't sabotage, it's calibration. Progress comes from asking uncomfortable questions. Do we actually understand this? Science stopped being an answer factory. It became a self-correcting journey. Ideas are proposed, challenged, refined, questioned again. Not because science is broken, but because that's how knowledge advances. As another saying goes, the map improves because we keep redrawing it. And physics is no exception. We began with an almost comical rumor. A physicist whose presence supposedly doomed laboratory equipment. Colleagues joked that experiments failed simply because he walked in. Yet history remembers something very different. Not mishaps, order. Because the man teased as an experimental jinx left behind one of nature's strictest organizing principles. Electrons stopped behaving like a free crowd. Atoms gained structure. Matter gained reliability. The universe gained stability. Possibility was constrained and reality became durable. There's a beautiful irony there. A man associated with chaos became an architect of cosmic discipline. And the story circles back to where it started. Real power doesn't live in colorful anecdotes. It lives in the rules that let the world hold together. Pauli didn't just make electrons follow the rules. He reminded scientists to do the same. Because science moves forward not by avoiding mistakes, but by refusing to let them slide. And that discipline, quiet, relentless, uncompromising, is what keeps discovery honest. The people who change the world usually just think one step deeper. If this story made you see things differently, hit like, subscribe, and save it. See you in the next story.